This is another edition for our lecture videos on multivariate calculus, and today I'm going to look at chain rule in multivariate calculus. With a quick recap, I'm looking at the single variable calculus one where we did chain rule. It says that if I have a function z, which is a function of x and then t, what this illustrating is that z depends on x and x depends on t. So I can find the small change in z respect to t given at equation 1 here. We already know this in single variable. Now in the case of multivariate, how do we find the chain rule, which is a function of functions, composite? In the multiple variables, I will have z depending on x and then y. That means multiple, where x also depends on a variable called t and y also depends on that variable t. How do I find the chain rule? It is mostly cool if you have the tree diagram. This is how we go by the tree. So I have z depends on x and then y, and x depends on t and y depends on t. You can take a cross section in this form. You realize that to be the same as this guy here, and so I can find the z dt as the small change. Let me clean this circle. Because it depends on two variables, I can't use the z dt dx as I did in equation 1. No, because it is two independent variables. The correct notation has to do with partial. So partial z, partial x. If I move from z to x, it is partial. Z to y is partial because it's 2. But if I'm moving from x to t, it is a total derivative. It is a total derivative here because it's one variable. So partial z, partial x times the x dt plus partial z, partial y times the y dt. I can rewrite this as partial z become z respect to x and then x prime plus z respect to y and then y prime. Y primes are the total derivative. So this is how simple the chain rule of z prime would be, z prime of t would be. So let me say equation 2. Okay, respect to t. And in the case where I have x depend on 2, it depends on 2, y depends also 2 different variables. Let's look at the tree. Z depends on x and y. So if I'm moving from z to x, I have partial because z has 2 independent variables. If I'm moving from x to u, it can be total because x depends on 2 variables. So I have partial here and partial here. The same thing for y, partial, partial. It can be total because I have z depends on 2 independent variables. X and y also depends on 2 independent variables, u and then v. So it has to be partial derivatives, just as we did in partial derivatives here. So the change in z respect to u, I'm looking at this angle. It becomes partial of z respect to partial of x times partial of x, partial of u, plus, and I can take that of the same u here, partial z, partial y times partial y, partial u. I hope that is so clear. I can rewrite this as z subscript x, x subscript u because it's partial, plus zy yu, and this is z respect to u, partial derivative. So I can simply write z respect to v also as zx zv plus zv yv, equation 2, 3a, 3b. This is how I do the tree diagram. In the case where you have more than 2 independent variables, I can still draw the tree diagram as you see here. Z depends on x, y, and then z. So if I'm moving from z to x, partial here, partial there, partial there. And then same if I move to any of the independent variables down here, it can only be partial, not total, because they have 3 independent variables. There's no total derivative anywhere. Everything is partial. So let's take respect to u. Respect to u becomes, here's f. I have f respect to x, x respect to u, plus f respect to y, y respect to u, plus f respect to z, z respect to u. I can rewrite this as f subscript to u equal to fx u xu, fy yu, fz zu. This is a partial derivatives. So know when to use partial, know when to use total. So let's take a quick example. Example 1. I see z depending on x and then y, and x depends on t, y depends on t. So I know that this will be partial here, partial there, but moving to this becomes total, total, d. So the z dt becomes partial of z, partial of x, x dt. No, now it's no more partial, so you be careful here. It is the total derivative here, plus partial z, partial y times dy dt, and every other variables are defined here, so you just take it. So I have z prime is equal to 2x here times the x dt. I come to this column, that will be 2, plus the z dy I move here, that is 1, times dy dt I move here, which is 3. So I have 4x plus 3. Now I can't leave my answer here because I'm looking at the derivative with respect to t. So I have to change all other terms to t. And how do I do that? I already know the formula for x, which is 2t plus 1 plus 3. And this will be equal to 8t plus 4 plus 3. That is giving me 8t plus 7. So this is the correct answer. If you leave it here, there's an error. So the final stage is this. This is method 1. Someone can also use it this way. If I want the z dt, I know it is partial z. Let me just use the shorthand. Z prime of t becomes zx, x prime of t, plus zy, y prime of t. Someone will first do a substitution of the z in terms of t's. So I have x squared plus y, and I know x is the same as 2t plus 1 square plus y, which is 3t minus 1. I do my expansion here. I'm going to get 4t square plus 4t plus 1, 3t minus 1. Simplification, 4t square plus 7t. This goes to 0. Okay, so this is z of t. That means that now z prime of t becomes 8t plus 7. This answer is the same as what we had up here. So it depends on you what you want to do. Do you want to first, so this is method 2. Method 2 say first do your substitution of your terms before you go ahead and differentiate. But method 1 says that, let me say method 1, it says that differentiate and then do your substitutions. Which one do you think works best for you? You choose it. But I would prefer to go with method 1. I want to differentiate before I do a substitution. That is better for me than doing the substitution and differentiating. But at the end of the day, you get the same answer. Okay. The last example, example 2. Always draw your tree. I have Z. It depends on variable X and then Y. And X depends on U and then V. Y depends on U and then V. Then you know how to do your partial or total. Because Z depends on 2 variables, I can't be total, I can only be partial. And because X depends on 2 variables, it can be partial at both ends. So there's no total derivative anywhere. So my partial of Z respect to U becomes partial Z partial U times X, and then X U plus respect to Y, Y and then U. This is the same as writing ZX XU ZY YU. So let's do that. If I differentiate Z respect to X, I get 6X minus 2Y. So this is it. And X respect to U, I move here. That'll be just 3 plus Z respect to Y is this portion. I'll get negative 2Y, no, negative 2X plus 2Y times Y respect to U, I move here, which is 4. And I do my expansion. I get 3, 6, 18X minus 6Y minus 8X plus 8Y. I hope my expansion is correct. And so in the nutshell, I'm going to have 10X plus 2Y. This is Z of U. But you realize the terms are in X and the Y, but I need in terms of U, so I have to do a substitution. So 10 into bracket, X is giving us 3U plus 2V. 3U plus 2V plus 2 into bracket, Y is giving us 4U minus V. Expand 30U, 20V, 8U, 2V. And that's going to give me 38U plus 18V. And that is my answer. No, wait. Yeah. So this is Z respect to U. Or you can go by method method 2. You do your substitutions first, but you realize that'll be so much cumbersome work to do. Let me try it out. Let me try that out. Z was giving us 3x squared minus minus 2xy plus I think y squared, and X was giving us 3U plus 2V, and Y was giving us 4U minus V. If I want to do a substitution of X and V first, see what I'm going to get. 3U plus 2V all square minus 2 times 3U plus 2V times 4U minus V minus, plus 4U minus V all square. You have to expand all these before you come and do the derivative respect to U. This looks a bit convenient, but then it's cumbersome, so I wouldn't prefer this method even though I'm supposed to get the same answer. So I prefer going through the derivatives first and then doing the substitution, but either ways you should get the same answer. And this is how simple your chain rule is. Always draw your tree diagram and know when to use the partial and when to use the total. All right, thank you very much.